Hello everyone, my name is Marcin Strojecki and I work at the Jerzy Haber Institute of Catalysis and Surface Chemistry Polish Academy of Sciences in Krakow. During my presentation, I am going to talk about the use of acoustic emission for assessing the climate-induced risk of mechanical damage in stave churches, showing especially examples of two stave churches in Norway, Hedal and Ringebu, which were the case studies monitored within the Symbol project. The issue we wanted to address during this research project is very often present in historical interiors, especially in churches where heating systems were introduced in order to increase thermal comfort of people during services in cold seasons. Heating episodes like this shown with the red color in the graph on the right, taken from the microclimatic data recorded in Ringebu Church, lasting several hours and increasing the air temperature by several Celsius degrees, always result in drops of relative humidity which are 2-3 times higher. Such a big RH variation are very bad for all objects made of hygroscopic materials, as they are susceptible to mechanical damage due to their dimensional changes related to shrinkage and swelling. It is especially important for wooden massive elements like sculptures, for which the risk of mechanical damage results from dynamic gradient type water vapor diffusion through the whole volume of the object and resulting in homogeneous distribution of stresses. So the natural question related to above-mentioned problem is how much environmental instability is actually safe for RH-sensitive objects. Typically, the usual approach to answer this question is indirect, by seeking correlation between environmental instabilities and damage observed, basing on the environmental data recorded during on-site measurements. In our case, the acoustic emission method, which was chosen and adapted to specific needs of remote long-term monitoring, traces the environmentally induced damage directly in specific object at the micro level. The idea of acoustic emission method is very simple and based on detection and processing of the sound and ultrasound waves resulting from the crack propagation, relaxing mechanical stresses induced by dimensional response of material due to its hygrothermal interaction with fluctuating environmental parameters indoors. These sound waves are detected on the object surface with the use of sensitive microphone attached. Then, these mechanical vibrations are converted into an electrical signal which in turn is amplified, filtered, and after digitalization is stored in the computer to be analyzed in the post-processing phase. The method is very sensitive, which on one hand is the advantage because very small damage can be detected before it's big enough to be spotted during visual inspection, but on the other hand it makes the long-term monitoring very difficult since it requires effective elimination of ambient background noise, which is especially important in objects which are used by people on the regular basis. Acoustic emission method has been introduced to monitor heritage objects since 90s of the previous century. However, the biggest development, both in terms of hardware equipment miniaturization and computer-aided software for analysis, took place over last 10 years. The method has been successfully applied in many heritage science research projects for various types of wooden artifacts, including objects of decorative art like massive sculptures, as well as everyday use objects like instruments, furniture, and chests. The results obtained during these projects, as well as conclusions drawn from them, were utilized, for example, to support difficult decisions while introducing the new climate control strategies like in Furniture Gallery at V&A Museum in London or in the National Museum in Krakow, or while introducing the conservation heating as it was in case of Knoll House in Sevenoaks. During Symbol project, Two case studies were selected for acoustic emission monitoring. Church in Hedal, located in the southern central part of Norway, and church in Ringebu, located in the central part of Norway. Both churches are equipped with local electric heaters, and both of them are heated in winter seasons. However, each of them has different heating strategy. This can be graphically explained on the next slide. Here in the graph on the left, an indoor microclimatic data covering 18 months period from 25th March 2019 to 25th September 2020 are plotted. The difference in heating strategies between these two churches is especially evident from the plots of temperature in the bottom parts of both graphs. In both cases, the heating period starts in November and ends in May. In Hedal Church, however, the temperature is kept between 6.5 and 8.5 Celsius degree, while in Ringebu, heating episodes elevating the temperature not higher than 20 Celsius degree are strictly related to church services. The lower limit of temperature is -5 Celsius degree. In consequence, resulting RH fluctuations are much bigger in Ringebu. Examples of such big and sudden events are presented with lime color in the right graph, where 2 weeks of microclimatic data recorded in winter period in both churches were shown enlarged. Apart from the microclimatic data, there was also CO2 concentration indoor monitored. Decay profiles of this tracer gas exhaled by people during services and visits is often used to identify patterns of use of object as well as to characterize the tightness of building envelope. Using graph shown here, where the data recorded in Hedal Church are presented, it can be seen that in our case such approach allowed identification of liturgical services linked with heating episodes. This procedure was also helping during the analysis of the acoustic emission data, as all identified acoustic emission events not related to object damage and occurring during people presence could be effectively filtered, taking into account their acoustical activity interpreted in such cases as the background noise. In both churches, massive wooden elements, construction columns located in the front left parts of the church, have been selected for acoustic emission monitoring. Acoustic emission sensors were installed with the assistance of conservation professionals using minimally invasive techniques with the help of elastic stripes and drawing pins pounded to non-original wooden parts which have been replaced during previous conservation interventions. In case of Ringebu, the second acoustic emission sensor have been attached to the outer part of the hand of wooden sculpture, which was selected after discussion with conservation professionals as one of the most problematic from the conservation point of view, damaged and susceptible for further damage progression object. In case of Hedal, the second acoustic emission sensor have been attached to some other construction element, which was one of the original wooden board of the internal wall, located about 1.5 meters from the floor level directly above the heater. This sensor was intended to monitor possible acoustic emission signals induced by this heating source. However, after some time of monitoring, it turned out that this acoustic emission sensor have been recording very big acoustic activity, spread in time and at the first glance not random, but at the same time not related to any potential external source responsible for object damage. Therefore, after period long enough to have sufficient data to make a reliable statistic, it was decided to move sensor 1 from the column to some other board in the same wall several dozen centimeters from sensor 2. Due to potential risk of fire, as well as to meet the fire safety regulation obligatory in stave churches, in both cases acoustic emission systems were placed and closed in special metal boxes. Apart from the fire protecting function, they also acted as an aesthetic enclosure hiding all of equipment including messy cables. In this graph, all results measured during the whole monitoring period from November 2019 till February 2021 are shown. Individual acoustic emission events, after digital filtration and elimination of spurious noises, were then binned in the hourly packets and presented as vertical bars. A lime color corresponds to sensor 2, which records signal from the board wall in position 1, while magenta and orange correspond to sensor 1, recording in the first phase of the monitoring acoustic emission signals from the column, and in the second phase from the board wall in position 2. Acoustic emission results were correlated with the microclimatic data recorded in the same period, shown in the upper part of the plots as red curve for temperature and in blue for relative humidity. The consecutive steps of data elaboration is presented in the following slides. As it was said previously, the source of acoustic emission signals originating from the crack propagation of wooden objects is the process induced by water vapor diffusion. Since diffusion in solid material like wood is not instantaneous, there is so-called response time, characteristic for specific object and related to its thickness, permeability and direction of cut. For that reason, in the first step of analysis, different moving averages of RH shifted in the time by the length corresponding to this response time were calculated. In the upper part of this graph, there are three different moving averages of RH shown as gray curve, plotted as blue, red and black curve, and corresponding to 2 week, 3 weeks and 1 month response time. To continue with further analysis, these moving averages have been discretized to be able to link individual acoustic emission events to the adequate increase or decrease of RH to specific level. In the next step, using calibration procedure performed usually in the laboratory experiments, it is possible to quantify the acoustic emission events expressed in little informative arbitrary units to the equivalent of surface area damaged expressed in squared millimeters. As response time of monitored object is unknown, it can be more or less estimated only. In this step of the analysis, possible correlation with consecutive moving averages are checked. It can be seen on both graphs in this slide, where on the left the mean acoustic emission energy corresponding to step of RH to the specific level is shown, whereas in the right graph an equivalent of surface area damaged plot in a cumulative form with the reference level of 60% corresponding to yearly average of RH is shown. Additionally, on both sides of this graph, the final values of this cumulative damage presented in graphical form is also shown. As can be noticed, there is no significant difference between these three distributions. However, there is another aspect suggesting some problem with the data, namely zero values of the mean acoustic emission energy calculated for the lowest level of all moving averages of RH. The same problem in different form is also visible in the graph on the right. There is almost no increase of cumulative surface area damage from 50 to 40% of RH, where they should be the most expected. It is even better shown on this graph, where each cumulative surface area damaged is plotted for all three monitored objects. lime color for the wall in position 1, orange in position 2, and magenta for the column. Curves were also correlated with microclimatic data presented in the top part of the graph. The first striking observation is that cumulative surface area damage measured for the wall in position 1 is 2 orders of magnitude bigger than for the column as well as for the wall in position 2 after moving the sensor from the column to this position. The second thing which should be noticed, marked with gray areas, is that the greatest increase of the signal for the wall in position 1 have been recorded during both of the heating periods. These observations suggesting that the source of this intense acoustic emission activity was somehow connected to heating source in the close vicinity of the sensor 2. Therefore, in the next step of analysis, possible relation with temperature was checked. However, unexpected reversed correlation have been observed, suggesting some electrical interference which have not been effectively filtered out in the post-processing phase. To verify this hypothesis, an additional energy filtering have been performed. Results of this filtering are presented in this graph, where significant reduction of signals for the wall in position 1 can be observed. It is much better visible when take a look on the same result in cumulative form. In consequence, after this procedure of acoustic emission energy filtration, the level of surface damage for the wall in position 1 has been equated with the other two measured objects. Repeating the same procedure as it was presented on previous slides, for this filtered data we can observe a significant improvement both in terms of distribution of acoustic emission energy and cumulative surface area damaged, corresponding to step of average to specific level. In this form, these recalculated results can be easily and without any doubts read as an obvious confirmation of proved fluctuation concept, as well as they can be interpreted as follows. Every drop of average to the level lowest than yearly average linked with increase of acoustic emission energy results in formation of new surface of material damage. It should be emphasized that in this increase is not big. However, due to the great sensitivity of acoustic emission method, it is easy to be detected and traced. Similar analyses have been done for acoustic emission signals measured from the column, and in this case also the confirmation of proved fluctuation concept can be observed. However, comparing to previous results, some small acoustic emission activity related to slight increase of average from the yearly average can be noticed. This can be interpreted as compression sets of wood due to its swelling in high average, and related to this process the development of damage of the surface. In practice, plots like this on the right for the column or analogical from previous slide for the wall can be used as benchmark or what-if scenario while changing heating strategy. For example, in this case, to reduce the damage by half both in shrinkage and swelling, average fluctuations have to be reduced to plus minus 7% from the yearly average. Concluding, I'd like to underline the most important notes coming from my presentation. Acoustic emission sensors show very high sensitivity in detecting very small damage in real time. Technical developments in the acoustic emission method broaden its use for long-term monitoring of objects in their natural environment in safe and aesthetically unobtrusive way. Acoustic emission monitoring supports the development of climate control and heating strategies based on the specific needs of the monitored object. And finally, My personal acknowledgements goes to institutions for their financial and technical support, as well as to people which especially help within the symbol project. Thank you.